Hello. So welcome back to the week part 2 of the week 6. And in the previous week, we talked about the recursion, right? And this recursion is a particular type of programming which has function within inside of the function definition. We call it the same function, right? So when you have to run something within this function, we encounter this recursive course, and this brings back to this function again with reduced size of problem, right? And in the middle, what we want to see here is that also we want to have a kooc, which is a escape routine, right? And this escape routine has an if statement, calls these parameters becomes what, then we are going to return, right? And then we are going to have this escape plan with this recursive course, right? And this is best applicable to the repeating problems, right? And repeating problems were defined as, right, we can make the same structure problem with the smaller version, and smaller version, and smaller version. This matches up perfectly with this recursion style, right? And the problem of this recursion, one thing is that sometimes we have to call the same function with the same parameter again and again. If we come up with the Fibonacci sequence in the last week, we could see that many functions were called repeatedly with the same parameter and returning the same value. And this dynamic programming is a solution to that, okay? And we are going to cover this in the second part of this week 6. In the dynamic programming, first we have to define this dynamic programming. Dynamic programming is a general algorithm design technique, which is the same thing as a recursion, but in a different structure. So to solve these problems defined by or formulated as recurrence, so it means that somehow we are dealing with recursive problems and with overlapping sub-instances. Means that this recursion here, F4, to calculate F4, here F means the Fibonacci sequence, right? Sequence, and to calculate F4, we need to know F3 and F2, and we need to know the F3, and we need to know F2 and F1. To know F2, we need to know F1 and F0. F1 and F0 are predefined in the problem set, right? So it means that we have a recurrence. F4 is with the same structure with the reduced parameter set. We have F3 and F2. Means that we have recurrence here. And this overlapping of instances. How many overlappings? Just one F4 and one F3, but we have two F2, right? And we have three F1, and we have two F0, which is like this, right? And we had to call F0 two times, F1 three times, and F2 two times, F3 one time to calculate F4, right? This context matches exactly same to the environment of the dynamic programming. So here we are going to call it. We are going to solve this problem with dynamic programming. So main storyline is this: we have to know the recurrence. We have to know the recurrence, and relating a solution of a larger instance to solution of some smaller instances means that it's just in the opposite way, right? Compared to the recursion. Recursion was a big thing and coming down to the size. And what we are going to do in the dynamic programming here in the main storyline is that we are going to create some smaller instances, some smaller versions of this. We calculate some smaller version of this, and we are going to make things grow. We are going to make things grow to reach a F4. we are going to solve some instances once. So we are going to solve some instances, smaller instances like the F0 and F1, which is quite easy to solve because it's already given. And we are going to record the solutions in a table like this, right? Table like this, and then extract a solution of a larger instance from the table. Means that if we already solved F0 is 0, F1 is 1, it's very easy to calculate F2 because that is the sum of the previous two solutions, right? Summation. And to calculate F3 is pretty easy because it's just a summation of the two instances before, right? This. How about F4? It's a summation of the two instances here, like this. So we get this number 3, right? So this is the main storyline. Previously, we have a question of the F4, and we were going to narrowing down, right? And here is the opposite way. We are going to solve these small problems, and we are make the solution grow, increases in terms of the parameter, and we want that parameter reaches a certain point. So in a really opposite way, solving the same structured problem, right? So that's the dynamic programming. Little more explanations. So we have a new term called memoization. It's memoization, yeah, it's not a memorization, right? So some might want to add R, but it's perfectly alright term without R, okay? So the key memoization is a key technique of dynamic programming, all right? So without memoization, we really cannot call it as a dynamic programming. To simply put, it's a storing the results of previous function calls to reuse the results again in the future, right? So it means that it just works like this. This is one perfect example of the memoization, right? So we have this table consisting of smaller sized solutions, and we want to fill in this solution table, memoization table, to reach a certain point, right? So that's the memoization table. More philosophical sense is that bottom-up approach for problem solving. Recursion is more top-down and divide and conquer way. And dynamic programming is bottom-up, and the storing and building the solution. So here, in two cases, recursion has this stack frame, right? When we call the F4, then we are going to call F3, and we are going to call F2, and so forth. So after we call F4, and we called F3, and F3 called F2. So it means that this stack frame indicates this stage, right? So that's the recursion way. And this memoization is that we solve F0, we solve next F1, and we try to solve this F2. And after solving F2, we already know the solution of F1, so it's very easy to solve F3, right? And it's very easy to solve F4 here, right? So it's really in the opposite way. So designing this memoization table is a key of this dynamic programming, right? Stack frame is already given in the MATLAB structure, in MATLAB the MATLAB programming structures, but memoization table we have to create it, okay? So this is how to calculate this Fibonacci sequence with the dynamic programming, right? So this is Fibonacci sequence in dynamic programming, and we are setting up all these things, right? So first, we have a memoization table, and the two things are here. So we have Fibonacci 1 as 0 and 2 is 1, right? And here it means that 1, 2, 3, 4, 5, 6, 7. This is index wise, and this is, if we call it number, 0, 1, 2, 3, 4, 5, 6. Because in MATLAB, the index starts 1. And the solution is that we are going to store 0 and 1 here, right? And from 3 to the n means that n is the input, the fn. And what we are going to do is that we are at this I, right? We are pointing at this index, and Fibonacci minus 1 and minus 2, add them and put the value here, right? And then ITR increases to point at 4, number 4. And then what we do is that we look at the third one, we look at the second one, add them, right? Add them and put it here too, and 3 and 5 and 8 and so forth, right? So this is the place where uses the Fibonacci sequence memoization table, and then make this solution grow, increases. This is for building up a bigger solutions, right? So use an array variable type for the memoization, and memoization is storing a Fibonacci number for a particular index, right? So this is a perfectly okay memoization table. Right? And now we have a new space requirement, the table order of n. In the previous recursion program, if you go back to the recursion program, we didn't need any arrays for that solution type, for that programming. However, here now we have a new requirement. We have to have this table which will require order of n space, right? At the same time, we are going to reduce that execution time from order of 2n to the order of n, right? Right. So whenever we have a certain F4, we had two child, right? Two sub-instances. We have two sub-instances to solve this, right? However, so it means that we have to calculate this and this and this means that 1, 2, 4. Exponentially grows, right? Right, yes. However, this order of n is just a n iteration, right? This is n iteration, and this is order of n, right? Means that this is much more time efficient. So we are sacrificing space-wise. This is the minus down term, and this is huge plus term, right? Because that nowadays the memory space is quite cheap, and we have SSD, we have hard drive, and we have so much spaces that we can acquire. However, the time just flows, and time is really golden, right? We really can't buy time with money, right? So means that if we can spend some money to increase our the memory space, we can buy this time, right? We can reduce this time constraint. This is a huge advantage for companies and for serious people who are using these serious applications, right? We are just dealing with the Fibonacci sequence, but if we go to the real world problems, then this will save so much money, right?